This presentation is by Dr. Freeman Jackson at Fourth Industrial Systems. Large language models, or LLMs, might seem like magic at first glance, but beneath the surface, they are built on mathematics, vast amounts of data, and intricate engineering. Today, we are going to break down the most common claims about LLMs, using real-world demos, practical caveats, and actionable takeaways you can use right away. Let us separate fact from fiction and see what really matters. You might have heard that a large language model is just two files, parameters and the code that runs them. While this is a helpful mental shortcut, it is not the full story. In reality, you also need a tokenizer to break down text, a configuration file that defines the model's architecture, and optimized kernels for speed. For example, files like model.safetensors, tokenizer.json, and config.json are all essential. Runtime accelerators such as flash attention, key value cache, and CUDA or metal support are also critical for performance. So to run an LLM efficiently, you need weights, a tokenizer, configuration, and an optimized runtime like llama.cpp or VLLM. There is a big difference between open weights and closed models. For instance, Llama 2 provides open weights, while models like ChatGPT are only accessible through a web interface. But remember, open weights do not always mean open source licensing. Open weights give you control. You can fine-tune, self-host, and use private data. Closed models, on the other hand, often offer better raw capability and more robust tooling. Your choice should depend on your needs for privacy, latency, and budget. Consider data sensitivity, customization, total cost, and service-level agreements when deciding. You might hear that a 70 billion parameter model at 2 bytes per parameter is about 140 gigabytes. That is accurate for models using 16-bit floating point precision, or FP16. However, you can quantize models to 8-bit or even 4-bit precision, shrinking them to sizes that fit on a laptop, with only a small drop in quality. For example, 140 gigabytes in FP16 can become 60 to 80 gigabytes in NT8, or even as little as 8 to 30 gigabytes in NT4. Tools like llama.cpp make it possible to load a 7 billion parameter NT4 model and see impressive token generation speeds. It is tempting to think you can just grab 2 files and run a large language model on your laptop. This is true for smaller models, but 70 billion parameter models usually require multiple GPUs or a lot of video RAM. For local experiments, start with 7 or 13 billion parameter models that are quantized. If you need higher throughput or longer context windows, server runtimes like VLLM are a better fit. Running locally gives you privacy, while server setups offer better throughput. Training a large language model is often described as compressing a huge chunk of the internet into a set of parameters. This is a useful way to think about it, but there are 2 important caveats. First, data quality matters more than raw size. Deduplication, safety filters, and contamination checks are essential. Second, because training is a form of lossy compression, hallucinations can happen. That means you should plan for retrieval and verification in real-world applications. The training pipeline involves crawling, cleaning, deduplicating, filtering, tokenizing, and finally training the model. Large language models generate text by predicting the next token, which means they sometimes invent details. For example, if you ask for an ISBN without grounding, the model might make one up. To fix this, add retrieval-augmented generation, or RAG, or use tools like browsers, calculators, or code interpreters to anchor answers. Always show sources and citations when possible, and use tools for math, code, or data tasks. We understand the mathematics behind the transformer architecture, but billions of parameters remain largely inscrutable. For example, the reversal curse is a behavior that is not fully understood. That is why interpretability research is so important, and why you should evaluate model behavior, not just architecture. Prompting tricks can sometimes mask real gaps in capability, so always measure behaviors directly. Turning a base model into an assistant involves several steps. First, supervised fine-tuning, or SFT, on high-quality instructions. Then add preferences using pairwise comparisons, and optionally use reinforcement learning from human feedback, or RLHF. Watch out for overalignment, which can lead to bland answers, and be aware of domain gaps. The process is pre-train for knowledge, SFT for format, preferences or RLHF for style, and tools or RAG for grounding. Large language models can call external tools to browse the web, compute answers, plot graphs, or generate images. Think of the LLM as a planner and the tools as actuators. Use tools by default for current events, math, scraping, or charts. Always sandbox and throttle tool calls to avoid unexpected costs. LLMs are not limited to text. They can turn sketches into websites or enable speech-to-speech conversations. Vision capabilities unlock code and user interface reviews, while voice features improve accessibility and hands-free use. Remember, prompts can hide in images, so always sanitize inputs for security. Sometimes you need to trade speed for accuracy. Use the slow mode. Plan, solve, verify, and revise. This costs more tokens but increases reliability, especially when combined with retrieval and tool use. Break problems into sub-steps, solve each one, verify with the tool, and then provide the final answer. Think of the LLM as the operating system kernel, orchestrating tools and memory. The context window is like RAM, and retrieval is like disk storage. Architect your application so the model coordinates tasks, manages context efficiently, caches results, and retrieves facts as needed. Security is critical. Jailbreaks involve tricking the model into breaking rules, while prompt injection means malicious inputs can hijack tool calls. Data poisoning can corrupt training data. Protect your systems by refusing and explaining jailbreak attempts, using adversarial training, and filtering outputs. Never trust inputs. Isolate tool calls, normalize encodings, and use allow lists. Control your data sources, deduplicate, watermark, and use evaluation suites to guard against poisoning. To build your LLM skills, try a 7-day sprint, run a local 7 billion parameter model, make a retrieval-augmented query, perform a tool call math task, and test a red team prompt injection. Patch any issues you find along the way. Remember, LLMs are prediction machines that need grounding. Tool use is their superpower, and security must be part of your design. Comment with what you will build this week and subscribe for a deep dive on retrieval-augmented generation and safe tool runners. Resources and links are in the description. Please remember to like and subscribe to Forth's YouTube channel.